So today we're going to do what I think is one of the more fun lectures. We have an interesting engineering problem to solve, and we'll actually come up with a nice, elegant solution for it, which is a pleasing combination. So away we go. So the problem we're going to tackle today is a little bit about how to do inter-process communication, or more specifically, how to arrange the synchronization between two communicating processes so that the operations performed by the processes happen in the correct order. And by correct, you'll see what I mean by that in a second. So this is something that happens pretty much all the time in computers. We're forever sending information from one place to another, and we have the notion of a producer that produces the information and a consumer that consumes it, and then information flows over this wire here from the producer to the consumer, and we actually have to coordinate the interactions between the producer and the consumer so that the producer doesn't overwhelm the consumer with too many things, and which might get lost depending on how much buffering we have, and the consumer doesn't try consuming things that haven't been produced yet. And you can say, well, that's sort of obvious, but remember, programs are pretty dumb. They'll just go get to a memory location and fetch whatever's there. So we're going to have to figure out how to do the appropriate signaling to say, please look here in this buffer that we're sharing as we communicate from one process to another, some sort of shared data or perhaps a pipeline of some sort. And what we want to do is talk about how each of these processes manage their end of the pipeline and communicate to the other process that there's something there to take or that something has already been taken. So it's really a signaling exercise that we're going to be doing today. And we'll come up with, as I say, I think what will be a reasonably elegant solution. So this type of producer-consumer problem crops up in most applications. For example, most of the applications that you run use a separate thread for the user interface, and the user interface produces a sequence of events that need to be queued up and processed by the front end, and then often, as in, for example, JSIM, there's a back end where the simulation is happening. So there's sort of the event processing, to the front end, and then from the front end to the back end. These are all sort of communications paths that have to be managed, and some amount of synchrony between the actions in one and the actions in the more background tests. Okay. So conceptually, imagine that the producer is running in a loop which does a lot of complicated calculation represented by XXX, and then occasionally it's going to send some information, maybe a particular character, to the consumer, and then it goes back and enters its loop again. And the consumer is in a loop where it receives a piece of information, so it will get the character that the producer sent, and then process it somehow, and when it's done with the processing of the communication, the message it just received, it will go back and look to receive another message. So these are the two, these are running independently, right? So the idea is that this is running in one process, this is running in the other, and there is a communication channel between them, which is maybe the shared memory location or the communication channel that will convey the characters, and the question is, what else do we need to convey? What other control signals do we need to have to organize the communication so it behaves correctly? So imagine time running down the page, and you can see what the producer is going to do is a calculation that produces the first character, which is then sent to the consumer, and then the producer, because he's in a loop, goes and produces the second character and sends that, so forth and so on. So here's time sort of running down the page for the producer. Over in the consumer, we see a receive followed by some calculation, followed by another receive. And what we're going to want to do now is explore, so each of these is sort of running independently, but there's going to be some relationship about what can execute when in one program and the other, one process and the other. So we're going to introduce a notion of precedes, this sort of what's called a precedence relationship. In this case, we use this fancy little sort of less than symbol to say that alpha precedes beta. So that's a very abstract way of saying, look, it comes before, and we want to ensure that happens. And so, in fact, there's two precedence constraints that we're interested in. The first one of which is that clearly you shouldn't receive a character before it's sent. In other words, we expect that the receive statement in the consumer will execute for the first time after the first time the send statement has executed in the producer. Right? So we want to somehow establish the precedence relationship that the first send happens before the first receive. And that's shown by the solid arrows here. There's a second relationship that we might want to ensure. In the case where we only can transmit a single character at a time, we have a very thin wire that goes between them. I can send you one character, but I'm not allowed to send anything more until you've consumed the first character. And so we might also want to introduce the precedence constraint that the second send has to wait until the first receive happen. And so what you can see is that we've established a series of precedence constraints that don't constrain when XXX happens, or YYY happens relative to XXX, relative to what's happening in the process. The only constraints about allowable execution orders are between the send and receive, and then the receive and the subsequent send. Everybody sort of get that? So what we want to do is to come up with some way in which the producer and consumer can signal each other, letting them know, okay, I've sent you a character, and then you as the consumer might want to signal me back as the producer that, okay, I've consumed the character, you can go ahead and do the next one. So we're coming up with sort of a way of managing our communication channel that's shared between us. That particular problem isn't so interesting, so what we're going to do is complicate it a little bit. We're going to introduce a first in, first out buffer between the two, so it has n characters. And what that allows us to do, so first in, first out means is, in terms of the consumer's point of view, when it asks for the next character, it will get the earliest character that's still in the buffer. So with a FIFO buffer, as the producer puts things in to the buffer in a certain order, the consumer, when it asks for things from the buffer, will get them in the same order that the producer produced them. So there's no mixing of order with the buffer. And by putting in this FIFO buffer between the producer and the consumer, we will allow the producer to get up to n characters ahead of the consumption. So if we had an n character buffer here on the table between me, the producer, and you, the consumer, I could put the first character there, and whereas before I had to wait for you to consume it because there's only room for one in the buffer, now there's room for n characters in the buffer. So I can go ahead and produce the second character and the third character, so forth and so on, up to n, and at that point I have to stop because I filled up the buffer, but it allows some elasticity between the running of the producer and the running of the consumer. So the producer might run for a little while, produce 3 or 4 characters, and then the consumer might consume a couple characters. So we don't have the producer and consumer quite in lockstep, and we allow an n character difference between where the producer is in its loop and the consumer is in its loop. Okay. So we're going to relax this precedence constraint and simply say that the ith reception has to happen before the ith plus nth send. In other words, we're going to let the send get ahead by n steps. Okay, but at that point you're stuck. Once you get to you've sent n things, you have to wait for at least the first reception to happen before you're allowed to do the nth plus first send. In other words, the reception has made room in the n character buffer for you to send one more character. So the way this might work is, so we have a read pointer and a write pointer. So this is a little circular buffer, which means we'll go through from right to left, and when we fill up the third thing, we'll go back and we'll just start filling up again at the first entry in the buffer. So that's what we mean by circular. It's just a fixed length buffer, and we have pointers that tell us where the reading is happening and where the writing. So we go off and we do a bunch of sends in a row, and you can see that the right pointer is busily advancing, and we're slowly filling up the buffer. And at this point, the buffer is full. So capital N is 3 in this case. Now the producer cannot produce any more characters. We can't do any more sends. We're sort of stuck waiting for the first receive. So the first receive happens, and you can see it has a separate read pointer that tells it where the next character to read is in the buffer. And so these pointers will basically just chase each other round and round and round the circular buffer, and hopefully won't lap. So the producer needs to stop when the buffer is full, and obviously the consumer needs to stop when the buffer is empty. But any other combination, they both have an opportunity to run. Now that the first receive has happened, or in fact a couple receives in this case, we can go off and do some more sends and some more receives. Everybody sort of happy with that let me go back to that sort of scenario, and notice that because we have an n character buffer, we can get up to 3 sends ahead of where the receive is. Okay? So here's some code that represents that sort of graphic on the previous page. So there's a shared memory which holds the buffer and the input and output pointers. So that's the thing we're going to, so the input and output pointers in this case are just an index into the buffer. So the index can go between 0 and n minus 1. Right, so that would allow me to access any one of the n locations in the buffer, starting with index 0 and ending with index n minus 1. Once I get to index n minus 1, the next index is back at 0 again. That's what we mean to be circular. And you can see that constraint is forced down here. We increment the index, in this case the in pointer is the right pointer, telling us where we can write into the buffer. And when we increment it, we do it modulo n. That's what makes the whole thing circular. And the consumer, which looks very much the same, goes off and it reads a character from the buffer using the output index, and then increments the output index modulo n. So that's what the producer and the consumer look like. Now, left to their own devices here, there's nothing that controls the execution here. There's nothing that's enforcing any of the precedence constraints. So what we're going to do now is to slowly evolve this program to include a mechanism for enforcing the precedence constraints that we want. Okay, so no precedence constraint. The receive could happen at any time. It's happy just to read from the buffer and increment the output pointer, whether or not the producer has produced anything. So there's probably a bunch of things we're going to need to fix up here.